Welcome, everyone. My name is Erin Hester, and I am the UC Merced Campus Associate Director for the Center for Information Technology Research in the Interest of Society and the Banatao Institute. Welcome to the 14th year of the CITRIS Research Exchange Seminar Series. We have in the past hosted a remarkable lineup of technology innovators in person at Siddhartha Hall in Berkeley, and we're glad to see all of you joining us here virtually for the Fall 2022 series. Before we begin the talk, I would like to highlight a few upcoming CITRIS events that you might be interested in. The first is the next CITRIS Research Exchange, and that's a week from today on October 19th from 12 to 1 p.m. for a discussion on PG&E's approach to balance resiliency, reliability, decarbonization, and climate change with Sumit Singh, the EVP and Chief Risk Officer and Interim Chief Safety Officer for the Pacific Gas and Electric Company, what we know as PG&E. Please make sure to check the CITRIS webpage for registration details and further updates to this event and upcoming events. I would also like to give everyone some virtual participation guidelines before we get into today's exciting talk. First, please post all of your questions on the question and answer or Q&A box on Zoom. You should see a little Q&A icon in the Zoom toolbar of your session. You can click the thumbs up on a question, which will help bring that question to the top of the Q&A windows for myself, the moderator, to see which questions the audience is most interested in. Questions will be addressed at the end of the talk. Today, it is my great pleasure to introduce Ricardo de Castro. He received his licenciatura and Ph.D. degrees in electrical and computer engineering from the Faculty of Engineering at the University of Porto in Portugal in 2006 and in 2013, respectively. After receiving his first licenciatura, he was an entrepreneur from 2007 to 2008 in the WeMoveU project, where they targeted the development of powertrain control solutions for lightweight electric vehicles. From 2013 to 2020, he was the German Aerospace Center DLR Institute of System Dynamics and Controls, where he developed enabling technologies for an electric mobility and automated driving. In 2021, he joined the University of California, Merced, where he is now working as an assistant professor and advancing his research. It is my great honor to welcome Ricardo de Castro.
Give me just 1 second. I'm trying to figure out the screen to share. So hello everybody, welcome to my talk, which is going to be dedicated to electric propulsion in agricultural vehicles, particular tractors. So in the next minutes, I would like to share some of my thoughts about the opportunities that this technology provides, and also some of the challenges and barriers that we need to overcome in order to make this a reality. And before jumping into my talk, let me also thank CITRIS for the kind invitation to be here today and to share my thoughts about this problem. A bit of background: where do I come from, what I've been doing in the last years. So I come from Portugal originally. I received my degree in electrical and computers engineering in 2006. And after that, I decided to create a startup with a few colleagues. The focus of the startup was to develop the first generation of motor controllers for neighborhood vehicles like the one you see here. And I learned a lot. I had the chance to build my first EV prototype. And then a few years later, I returned to the university to pursue a Ph.D. During that time, I was focusing on hybridization between high energy batteries and high power supercapacitors in order to reduce the mass of the battery in order to improve the energy efficiency. And during that time, I built my second EV prototype that you can see here in this picture. We used to joke that the car is red from the outside, but green from the inside. Then a few years later, after my PhD, I went to Germany and I worked for the German Aerospace Center, DLR, which is the German version of NASA. And I had the privilege to work with my third EV prototype depicted here, the WeMoveU, the robotic electric vehicle, which has a very unique powertrain. So each wheel has its own electric motor that is embedded into the wheel hub, also has independent steering actuation, and we have a high degree of maneuverability with this prototype. And this was a great research toy that I exploited during my time in Germany. Then last year, I moved to California and I started an academic career here at UC Merced as an assistant professor in the Department of Mechanical Engineering. When I arrived, I realized that the campus is surrounded by farms. We are in a very rural area. Most of the vehicles that I see in the farms nowadays, they still run with internal combustion engine. And so there is a huge opportunity and necessity to decarbonize this sector. And the next stage of my career, I would like to dedicate to find practical ways to bring electric powertrains to the farm. A bit of background regarding EVs on roads. Very likely, some of you already drive an EV. There are also not just passenger cars, but also other types of vehicles are becoming electric. Light-duty trucks. You might come to campus using an electric bus, and so there is a lot of traction going on with the electrification of road vehicles. Also, in terms of sales of road vehicles, this year, more than 13% of all sales are going to be of EVs. And the forecast for the next years is of a tremendous growth. But there are other types of vehicles that we need to use, and they don't operate on roads. They operate off-road. Some of the examples you can find in construction sites, in mining, forestry, agriculture, which is the focus of today's presentation. And in comparison with road vehicles, you don't find many off-road EVs. Also, in terms of adoption, we are still lagging way behind what is happening on the road. And so that's the main motivation for today's talk, is to look more into this sector, and in particular into the electrification of farm vehicles. So my presentation is going to be divided into three main parts. At first, I'm going to talk about why it's a good idea to electrify tractors, some of the challenges, some of the opportunities, and I'm also going to present one of the main research questions that I've been looking in the last months, which is I want to understand under what conditions an electric tractor can be affordable than a diesel, especially when you take into account the entire lifetime of the tractor. So not just the purchase price, but also operation and maintenance costs. And in the second part of the talk, I'm going to say a few words about the methods that we are using to address this question, some of the operational requirements that we need to understand for the tractor, some of the simulation models that we are using to predict the performance of the tractor. And then at the end, I'm going to share some of the techno-economic results, some discussion, and outlook for future work. So tractors are used in farms, and more than 50% of all the land that we have here in the US is dedicated to agriculture. So it's a big sector. And tractors are used in farms in order to provide power to a wide range of agricultural tasks and operations. So usually you attach an implement to the rear of the tractor, and depending on the implement, you can be supporting different types of tasks, ranging from tillage, weeding, fertilizing application, harvesting, and also shuttling of crops from one side to the other. And there are plenty of tractors here in the US. More than 4 million tractors exist here in the US, and most of them, they still run on diesel. And so they generate emissions, they have all kinds of issues, as we will see in the next slides. And so it is a necessity for us to start thinking about electrifying these kind of vehicles. Tractors, they come in different shapes, different forms. You can find them in garden. You can also acquire compact or utility tractors, which are a bit smaller and are usually very effective, for instance, for orchards. You can also go a bit bigger for row crops and also industrial tractors for big and industrial farms. You have different types of locomotion, wheels, tracks. Lately, you also have autonomous tractors that are being developed. And so there is a wide variety of options, but most of them, they still share a common feature, which is a diesel engine. And in this slide, you can see simplified representation of the powertrain of a conventional tractor with a diesel engine. So coupled with the engine, you have the mechanical transmission, a gearbox that provides power to the wheels. You also have an additional interface to transfer power and energy to the implement through the PTO, the power takeoff. And you might also have very likely an hydraulic system inside the powertrain. And what I would like to discuss today with you is why not replace the diesel engine that you have in the tractor and bring an electric motor and supply energy to the tractor using, for instance, a battery instead of burning fuel. And it's not just acquiring the tractor, you also need to think about how you're going to charge. We're also going to look into the charging problem. And so now I'd like to address the question, why should we electrify the tractor? One reason is related with air pollution. And so diesel and internal combustion engines, they generate CO2 gases that affect global warming. They generate particulate matter, nitrogen, oxide, NOx. In particular, this last gas is something that can cause respiratory illnesses among humans, and it's a big concern. And in this plot here, you can see the average NOx emissions here in California over the last 20 or so years. And you can also see different sources for these emissions, ranging from on-road, heavy-duty, light-duty vehicles, stationary, and also off-road vehicles. And the positive trend that you see here in this plot is that these emissions are going down. But if you look closely into this plot, you can see that the pace at which the emissions of off-road is happening is a bit slower than the reduction in other sectors. And in fact, off-road vehicles are on track to overtake road vehicles as the main source of NOx, which is going to be a big problem. And so electric tractors can help us bring these emissions down. Then another dimension is related with policy and regulations. Perhaps you heard a few weeks ago, California announced the ban on the sale of cars with internal combustion engine by 2035. There is also an executive order from our governor that expresses the desire to transition to 100% zero emission off-road vehicles also by 2035. But there is a catch here, which is for off-road, this is not yet mandatory. It's only where feasible, because it's a bit more challenging to electrify these vehicles. In any case, electric tractors, they are and they will be compliant with some of these upcoming regulations that we start to see here in California. Energy efficiency. Diesel tractors are not very efficient. In fact, most of the energy that you put into the engine is lost into heat, and a modern diesel tractor does not offer peak energy efficiencies higher than 40%. So most of the energy you put there is lost. This contrasts with the high energy efficiency that you can obtain from an electric motor and an electric tractor. modern electric motors, they can offer peak energy efficiency higher than 90%. So it's completely the opposite. Most of the energy you put in the motor is used to develop useful work. And that's a big advantage of electric tractors. Additionally, we should also look into the noise. And to understand that, it's convenient to look into this noise scale using dBs as decibels in the scale. So we start at 0 dBs, which is the softest sound that we can hear. And this goes all the way to 120 dBs, which is something that you might be exposed if you go to a rock concert. And a diesel tractor generates noise in the range of 95 to 105 dBs, which is pretty significant. And according to CDC, if you are exposed to noises that are higher than 100 dBs for 5 or more minutes, you might develop risk of hearing loss. And so you can imagine a farmer, workers that are in the farm, they are exposed to this kind of noise all day. And that's a problem. On the other hand, when you look into electric tractors, they are quieter. In fact, they generate a noise that is slightly higher than my voice pitch right now. And so that's much more friendly when you think about interacting and working around the tractor all day. And they can also facilitate, because of their low noise, low emissions, you can also use electric tractors in indoor operations, which is much more challenging when you have a diesel tractor. Then going into the maintenance and repairs, as you use the tractor, there are components that are going to break down, they are going to wear out. And so you need to cover the costs for these maintenance. And in this plot, you can see the average repair costs of a diesel tractor as function of the number of working hours. As I expect, as you use the tractor more and more, the maintenance costs are going up. And in fact, if you are a heavy user of a tractor, it's not uncommon to see 50, 60, 70% of the purchase price goes or it is used then for maintenance and repairs, especially if you take into account the entire lifetime of the tractor. Now, looking into the electric powertrains usually have less number of moving parts, especially the engine, and that contributes to a reduction in the maintenance costs, especially of the mechanical powertrain. And there are several studies that indicate that the electric powertrains can offer lower maintenance costs, up to 50% in some cases of cost reduction in M&R. But there is a catch, which is at some point with an electric powertrain, you might need to replace the battery. And that offsets some of the gains that you have in the reduction of mechanical maintenance. Charging infrastructure is also another concern when it comes to electric tractors. The good news is a tractor normally doesn't travel far away from home. So that means you're not too far away from a charger most of the times. But the issue is you might need a significant amount of power to recharge the battery. And to have a better understanding of this challenge, let's assume that you own a 70 horsepower electric tractor that operates with 50% of the maximum power over 8 hours per day per charge. And under these conditions, you will need a battery that requires or provides at least 200 kilowatt hour of energy per day. And this is 2 to 3 times bigger than a battery that you have in a Tesla Model 3. And when you think about charging this battery overnight, you might need to acquire a charger with a peak power of 17 kilowatt, which is again pretty significant. It's 2 to 3 times, this power level is 2 to 3 times larger than the maximum power you extract at your home. And so when you start thinking about farms that are located in remote areas, these high levels of charging power might be a barrier for the widespread use of this technology. Also, large battery packs, they are also heavier, they're more difficult to integrate in the tractor, and there's also a drawback and a shortcoming of electric tractors that we need to consider. So this slide provides an overview of the pros and cons that you have with these different powertrains. So to summarize, electric tractors, they offer zero local emissions. They are compliant with the current regulations and very likely the upcoming regulations. They offer higher energy efficiency. They have low noise. And in terms of maintenance and repairs, they offer, especially at the mechanical maintenance, they can reduce costs on that front. Challenges are related with the charging infrastructure, so you might need to upgrade the electrical installation. Also, the energy storage, if you go with the batteries, they are bulky for this high power and heavy duty use, and are also acquisition costs because electric tractor is a new technology. Some of the components are a bit more expensive, like battery, and that will require higher purchase costs, which might not be so attractive for a farm. And so for the next minutes, I would like to spend now spend a bit more time talking about this total costs issue, and to understand under what conditions an electric tractor can be more affordable than a diesel when you consider the overall costs of ownership of having a tractor. So throughout the entire lifetime, not just during the acquisition, but also during the operation. And so that's the main question I'd like to address in this part of the presentation. So regarding the methods that we use to address this question, to motivate the methods, imagine that you are a farmer. You have a tractor right now in your farm, and you decide, okay, it's time to replace the tractor. And the question that emerges is, what type of powertrain is more suitable for your farm? Should I buy a new diesel tractor? Should I replace it with an electric? There might be also in the future opportunities to have hybrid powertrains that mix both. And so that's a question, practical question that is emerging now. And so how can we help the farmer decide about the best type of powertrain for his operation? So to address this, we are designing and building a decision aid tool that can guide and inform the farmer making this decision. And so this decision tool is divided into three main blocks. So in the first, we have a pre-processing block that collects data from the farm, collects data from the tractor, and captures the operational requirements for the new tractor. In the second part, we have a simulation model that predicts the behavior of the electric powertrain, of the diesel powertrain, and we have better understanding about the expected fuel consumption or energy consumption of the tractor. And then at the end, we have a techno-economic analysis, which produces some performance or evaluation metrics, including total costs of ownership. So not just purchase price of the tractor, but also fuel, energy costs. We also have other metrics for emissions, which might be important, not only for the farmer, but also for governmental agencies to show that we are decreasing these emissions. Okay, so that's the overview of the decision tool. Let's now have a closer look into these operational requirements that you need when you are thinking about replacing the tractor. So we need to decide what is the nominal power of the tractor. So in this study that I present here, I assume that the power is equivalent to the power we have right now in the farm. We need to understand how many hours you use the tractor per year, how many hours do you use the tractor per day. That will play a big influence in the size of the battery. And also very important is what kind of tasks are you doing with the tractor? Are they heavy lifting tasks? Are they light tasks? And we can capture these kind of requirements using engine load profiles. And to better understand this, I have here this plot, which represents in the horizontal axis, you have the engine load normalized with respect to the nominal power. And so that means if you have year one, it corresponds you are extracting the full power that the tractor is producing. 0.5 means you are extracting half of the maximum power, and so on and so forth. In the vertical axis, you can see the cumulative distribution of the engine load. And you can read this plot as follows. Imagine that you are looking into this blue curve, which corresponds to the engine load when you have a tractor in an orchard. And you see that 60% of the time, the tractor is using an engine load that is 20% or lower. So most of the time, the tractor is operating with light loads. And when you look into other curves, for instance, a row crop, you see that the tractor then starts to be used more with the medium and heavy loads. And so if we have access to this kind of statistical characterization of the engine load, we can then have a better understanding about the power and energy needs that the tractor is going to develop while in operation. So then based on this data, we can then construct operating cycles that we can then inject into a simulation model. We start first with a simulation model for the diesel powertrain. So we have a couple of metrics that we need to look into. We need to look into the fuel consumption or fuel rate of the engine. So we are using lookup tables to obtain this estimation. And we also need to predict the emissions of CO2, NOx, PM. And for that, we are using models, recent models from CARB that has been studying the emissions of off-road vehicles for a long time. And they have very practical models that we can include in our simulation framework. Then we do the same for our electrical powertrain. So we need to look into the power that is being requested to the motor. We take into account the losses that we have in the powertrain, which for the electric version are not that significant. And then we can estimate the amount of energy that the battery is deploying while in the field. Also very important is a degradation model for the battery, because as you go through the charge-discharge cycles, the amount of energy that you're able to extract from the battery decreases over time. And at some point, you need to replace the battery. And so in our simulation framework, we also have a simplified model that allows us to understand the time where we need to change the battery. And we also have another component that looks into the charging power. And that's also another important aspect to look into the operating costs of the electric powertrain. So that was the simulation model. Now let's look into the total cost of ownership. There are four main categories that we are using. We're looking into the vehicle costs, or the purchase price of the vehicle. We're looking into the energy costs, infrastructure, and there are other costs that also need to be taken into account. Regarding the vehicle costs, we need to look into the cost to assemble and build the chassis, the mechanical transmission, diesel motor, the electric motor, the battery pack. And so to account for these component costs, we are using some normalized cost metrics that we found in literature. Unfortunately, I don't have time here to go into too much detail, but if you have questions, we can address them in the Q&A about this section. We also need to take into account the taxes, the finance, in case you need to ask for a loan. Energy costs include diesel or fuel costs. and also electricity costs. So for diesel, we are assuming an average cost of $4.25 per gallon, electricity $0.17 per kilowatt hour. And we also assume an average increase in price of 3%, which is in line with some of the energy forecasts that we see from some agencies. Infrastructure costs include the charger and also include, it might include upgrades to your electrical infrastructure, especially in farms that are located in isolated areas. It might be necessary to change the cabling, changing the transformer, and we need to also consider that. Maintenance and repair, I assume that the electric tractor, the maintenance of the mechanical powertrain is 35% cheaper than with diesel because of the lower number of components. But we put on top the extra cost that you need to consider when you are replacing the battery midway through the life. And there are a couple of extra costs related with the housing and insurance. And in the study that I'm showing here today, we assumed that tractor has a useful life of 15 years. So let's look into some of the results that we obtain with this framework. So here you see the overall costs of ownership when the tractor operates with an engine load around 20%, which is pretty light. And when you use the tractor, 400 hours per year, which is again also not very significant. So in this operating scenario, the overall costs of ownership for a diesel powertrain are $98,000. And when we go electric, the costs they increase to 112, so you pay more 14%. And when you dig deeper into the cost breakdown, you see that in blue we have the purchase price of the vehicle, and so you are paying more upfront for your electric vehicle. You also have the extra costs with the charging infrastructure, and that's the main reason why the electric powertrain is not that attractive for this particular operating scenario. Now, imagine that you start using the tractor more and more. So instead of using it 400 hours per year, imagine that you are a heavier user, and you operate the tractor for 1,000 hours per year, or 1,200 hours per year, which is the case here that I depict on this side of the slide. And as you use the tractor more, the costs they increase. When you look here into the diesel, the overall costs now are $241,000. You see that now the fuel costs, they increase significantly, so they are very likely the main cost that you have with the tractor. And when you look into the electric powertrain, you see that the purchase price is still high, but the energy costs are significantly lower than the diesel. And because of that, we are able to reduce the total cost of ownership with the electric powertrain in 18%. And so that's an area where electric powertrain is very attractive. And we continue doing this analysis for trying to understand the different operating scenarios where electric powertrains pay off. And to help us in this study, it's useful to look into this indicator, this difference in the total cost of ownership between the diesel costs and the electric costs for different engine loads and for different hours per year. And you see that, well, before jumping into the discussion here, let me highlight that if these bars, this delta is positive, means that the electric tractor is more affordable. If the delta is negative, means that the diesel tractor is cheaper. And there are two trends that are worth mentioning here in this plot. The first is, as you increase the engine load, you need more power, more energy, you need bigger batteries and larger investments in the charging infrastructure. And you see that the bars, they became more and more negative. That means diesel becomes more attractive as we increase the load. The other remark that is worth mentioning is that as you increase the number of hours per year that you employ the tractor, then you have the higher fuel costs. And then there is the electric powertrain becomes more attractive and more competitive from an economic perspective. It's also useful to look into this sensitivity analysis from, let's say, or to identify the areas where the electric powertrain is more affordable. And we did that here in this plot. So we have, again, working hours per year, engine load. You see that electric tractor is more affordable if we stay with light loads. So around 0.1, if you increase the number of working hours, then you can start covering some of the medium engine loads. This star here represents the typical conditions, operating conditions for a tractor in California. And a tractor in California on average operates with 50% of engine load and operates 800 hours per year. And so what you can see is that the electric tractor as it is today is not yet able to cover and to reach, from an economic perspective, to reach the average operating conditions of a tractor here in the state. How can we improve the economic competitiveness of an electric tractor? One way to look into this is by reducing the hours that you have, working hours that you have per day. So for instance, instead of working 8 hours, if you just work 4, then you don't need to carry such a large battery with you. And so that means we can increase the operating area under which electric pays off, as it is highlighted here in this blue area. Also, another exercise that we can do is, it's expected that in the future, the costs with the batteries are coming down. And so when we reach, for instance, $100 or $50 per kilowatt hour, we expect that the operating conditions under which electric is more affordable, they are going to increase and expand. And when we reach these $50 per kilowatt, we will be able to cover the average operating conditions of a tractor in California. So we either work less with the tractor or we wait until the batteries become affordable in order to have, let's say, conditions under which electric tractors are more affordable. Now, there's also another dimension that we can't forget, which is related with the battery weight. And this plot shows what happens to the battery weight as you increase the engine load and as you increase the number of working hours. And these, the vertical axis represents the percentage of the battery mass with respect to the tractor. And so if you have heavier loads, you can start to have very heavy batteries reaching 50, 60% of the overall mass of the tractor, which is pretty significant. That puts a lot of pressure in the soil, might damage the soil structure, and might also have a negative impact in the crop yield. And there are a few alternatives that we can explore to address this issue. One possibility is to use, for instance, a wired electric tractor, a concept that was proposed a few years ago by John Deere. And essentially, you bring a cable with you. You can employ a very small battery inside the tractor, and you just rely on the power that the cable provides to you. Not very practical, but could be a first entry point of electric powertrains for big machines. Battery swapping is also another possibility. So imagine that you have 2 batteries, one that you use in the morning, another that you use in the afternoon, and at noon you replace and you swap the battery. So you don't need to carry such a large battery with you all the time. And another possibility that I would like to briefly touch today is related with the hybridization of the powertrain. So combining a diesel engine with an electric motor and an electric powertrain in order to exploit the best features that you have from each of these 2 worlds. So high energy density with diesel, high energy efficiency, and low emissions from the electric part. So when you think about hybridization, the first question that we need to look into is how big should the diesel engine be? How big should your battery be? And so to address this, we formulated a simple optimization problem that tries to find the sizing of the motors, taking into account the minimum total costs of ownership. We're also considering a hybrid powertrain that has a parallel architecture where you incorporate the motor in the same axle as the diesel engine, and that facilitates the combination of the both torques that these two machines produce. And so let's look into the areas where the hybrid powertrain is competitive from an economic perspective. And so the sweet spot for the hybrid powertrain corresponds to the medium loads, so something between 20 and 40%. And that's an area where hybrid is even cheaper than electric and diesel. And so when you dig deep into the economics, you see that in this plot here, we have the total cost of ownership when the load of the engine is 30%. We see that the hybrid powertrain reduces the overall costs in 2% when compared with diesel. It reduces the fuel costs in around 12%. And it also offers lower upfront costs for the farmer. So the cost of a hybrid tractor might be smaller than the electric. And so these are some of the reasons or areas where hybrid is attractive. We can also do another exercise and understand what could be the impact of the hybrid powertrain when we go to heavier loads. And this plot here represents the design trade-offs that you might need to face. In the vertical axis, you can see the total cost of ownership. In the horizontal axis, you have the emissions. So for 50% engine load, the diesel tractor is always more affordable, but generates lots of emissions. Electric is more expensive, but has zero local emissions. And I'm focusing here on NOx today. And you have the hybrid powertrain that provides a balance. And these dots here, they correspond to different sizes of the battery and the electric powertrain. So as you increase the size of the electric powertrain, you are able to decrease the emissions, but you need to pay more. And a potential good balance here could be, for this particular operating point, could be a hybrid or a electrification ratio of 30% here, where you decrease the emissions in 30% at the expense of 4% increase in the overall costs of the tractor, which could be a good trade-off as you go to larger machines. And this brings me to the conclusions of today's talk. So I introduce you and talk about the opportunities that you have with electric tractors to reduce air pollution, improve energy efficiency, reduce noise. Our study indicates that electric tractors are already cost competitive as long as you operate it with light loads and as long as you take into account the entire costs of ownership of the tractor. We also saw that as the battery costs come down, you might find many operating conditions where you have parity, cost parity between diesel and electric. We also looked into the hybrid powertrain where you combine both electric and diesel. And this could be an attractive option for medium loads. And it can also give you a good trade-off between costs and emissions as you go to heavier loads. For the future, I'd like to extend this decision tool and I'd like to incorporate multiple vehicles. I would also like to add more powertrains, not just electric and hybrid, but also fuel cells. And if you are going to buy an electric tractor, perhaps you're also going to make an investment in renewable energies. So I'd like to bring that dimension also to the decision tool. I hope I will have the chance to transfer this decision tool and to provide technical assistantship to the many farmers that we have here in Central Valley. And I also hope that this can be used to increase the readiness level of farms to transition and support electric tractors. I'd like to thank my collaborators, so Dr. Reze Sani and Ali Delaware from UC Merced, also Dr. Stravos Mugiokas from UC Davis, and acknowledge the funding that I'm receiving from CITRIS and also from Fresno Merced Future of Food Innovation Initiative that allows me to look into these exciting problems. A couple of final remarks. There are two events going on here in Merced and Fresno. So next week we have the FIRA USA, which is a conference dedicated to robotics and agriculture. There will be a strong involvement of industry, manufacturers of tractors, and if you are in Central Valley in Fresno, that will be a good opportunity to see what's going on in the industry. Then later, in early November, we are going to host a technical conference here at UC Merced dedicated to electric vehicles. Is the IEEE Vehicle Power and Propulsion Conference. We have several contributions in the organizing committee, members from different campuses, from Berkeley, Santa Cruz, Davis. We are going to have also a panel session dedicated to electrification of off-road vehicles. And this could also be another interesting event for you to attend, and I hope you can make it. So I think I'm running out of time, so thank you very much for your time and attention, and I'm looking forward to your questions.
Thank you very much, Ricardo, for the very interesting talk. And it's really exciting to hear about some of these developments and feasibility and where we're going. We have a watch party that's happening here live at UC Merced. So many of us are together in person watching this. And so the UC Merced live watch party asks, first they say great presentation, and then they have a question for you, which is about the future of work. And so, especially maybe for the students in the audience, but all of us, as we're thinking about what this future is going to look like, what are the opportunities for workforce development for electric tractors and the green transformation of agriculture?
That's a great question. So I believe that we need to train technicians, we need to train workers to be able to repair, for instance, these electric tractors. When you think about going not only electric, but autonomous, perhaps in the future, most of the tractors we're going to see in the farm, they're going to be autonomous. And you'll need engineers to build these tractors. You need engineers to manage them. And I believe that on the long term, that's going to be a shift. So instead of humans working in the farm, they will manage the tractors and robots that are doing the work for us. And I think that's going to be the long-term vision for the agriculture.
Great, thank you. So what would you, I'm going to have a follow-up question for that. For the students specifically in the audience, if they were interested in being part of this future workforce, what should they be focusing on now, either in terms of coursework or research?
So perhaps a great contribution if you are a student and if you have interest, let's say, in working for a manufacturer that is building now these electric tractors or is going to build in the future hybrid tractors or fuel cell tractors. It will be interesting for you to have a good understanding about energy storage, because that's going to be a key issue. So batteries, if you are in mechanical, for instance, thermal management of the battery is a big topic. If you are in electrical engineering, understand about the electronics. How can you control the motor? How can you manage the battery? And yeah, there are all kinds of interesting problems, and we need engineers, and we need the next generation of engineers that need to look and help us solve this, how to build an affordable and an efficient tractor.
So on that topic of the future, Josue Medin is asking us to, or asking you to maybe make some forecasts or some predictions about the load to hour distribution of tractors changing over time, and what is that going to look like as we try to approach this zero emission target?
So I believe that in the next 2-3 years, you will see the appearance of electric tractors in the farms. And from this preliminary study that I presented today, the entry point for electric tractors is going to be focusing on these light load conditions. So very likely in orchards, vineyards, that appears to be a good case study or a good use case to start with electrification due to the low loads. You don't need a big battery, you don't need a big charging infrastructure. Then in the future, when you go into medium and heavier loads, I'm not entirely sure if battery tractors are going to be the long-term solution for that. Perhaps we need to start to look into fuel cells and other types of energy storage capability that offer better energy density and are more practical.
Great. So then there's a question, thinking about energy density, what role do you think, this emerging technology of fuel cells and green hydrogen might play in this zero emission horizon?
That's a good question. I see there's a lot of interest in employing fuel cells for heavy duty, high power vehicles, especially on the road. So like trucks, there are several projects, several manufacturers that are looking into that. And one of the reasons is the high energy density that fuel cells can provide, which is great. But on the long run, there is also the problem of the charging infrastructure, because if tomorrow I buy a fuel cell tractor and I use it here in my farm, where I'm going to refuel it. And so they are also facing similar problems as the batteries. And it's not, for me, I have to say, it's not clear which technology is going to win on the long run. But I see merits in both of them.
Great, thank you. So Lee Bernacki asks, that she's really impressed that this is already a cost competitive technology. So what's it going to take to improve adoption?
I believe, again, the charging infrastructure might be a big barrier. So when you think about bringing this technology to farms, that are located in remote areas, I believe that the farmers, they will need to receive perhaps some kind of economic incentive or support from the state to alleviate some of this extra burden with charging infrastructure. So that might make things even more competitive and more attractive on the long run. There is also another instrument related with credits that the farmers can receive by offsetting emissions. And so there are some markets that now that are emerging. And I think this could also be another instrument, another incentive for the farmers to acquire this kind of technology.
We have a couple of questions emerging around the life cycle analysis component of your work. And so Briston Jones asks if you've, considered life cycle beyond emissions and really thinking about full life cycle assessment, and whether there are other places in the life cycle that we can target sustainability for these technologies. And then UC Merced student Arav Gupta, again, following on to that, again, thinking about that more complete life cycle, such as decommissioning of batteries or diesel components. Maybe you can share your thoughts on both a more complete life cycle and where you think we can improve sustainability.
These are great questions. So this is on my roadmap for the next months, because I started this study 5 or 6 months ago, so it's pretty new to me. And so one of my objectives is to also bring this life cycle analysis, in the sense that there are also emissions when you are building the battery that you need to take into account. There are also emissions even when you are using electricity. It depends how you generate. And so I also want in the next months to bring that kind of analysis into my tool. And I would love to cooperate with other faculty here at UC Merced, with students. So if you have interest in this space, I'll be happy to talk with you, because this life cycle analysis is not my forte. And so having other collaborators with that background will be really good to me.
So circling back around to this idea of like, maybe the challenge to adoption is infrastructure, and what is this going to look like in different places around the country and around the world? For example, Warren suggests that, on-farm solar power might be a viable route for some of these like large scale operations, which might even be bigger consumers of diesel than here in California, where, we don't have the largest tracts of land to deal with.
That's also a very interesting remark. I had some extra slides about how to incorporate solar with electric tractors. In fact, I'm collaborating with Dr. Sarah Kurtz here at UC Merced looking into this problem. And we realize that nowadays in California, the farms, they consume 300 million barrels of diesel per year. And with some back of napkin calculations, we estimate that if you put solar panels on 0.5% of the crop area here in California, that will be enough to power all the tractors that we have here in our state, 0.5%. And so I'm really excited. I believe that solar panels and agrivoltaics, where you use the solar panels not just to generate energy, but also to improve the crops, can be an enabling technology to charge the tractor. Especially it can provide opportunistic charging because the renewable source is there in the farm. So you can very easily access the energy that the solar panel is generating. And especially here where we are, Central Valley, it's very sunny, and it's definitely a great idea to accelerate the adoption of electric tractors here.
Right. So maybe a follow-up on that. I'm putting my IoT for ag hat on here. One of the big challenges for thinking about IoT-enabled precision agriculture is some of these edge technologies, both for communications and power. How do you think that, the electrification of our equipment might fit into a larger IoT infrastructure? And where do you see opportunities and challenges there?
That's also interesting. When I look at this from a macro level perspective, you might have multiple machines that need access to energy. So not just tractors, robots, drones, all kinds of equipment that is in the farm. And you might need to schedule when each of these vehicles is going to charge. So you need to communicate and need to plan when I'm going to charge this tractor or this robot. And I believe that IoT then could play a role in order to coordinate the access and scheduling the charging of these multiple vehicles and multiple tractors that we might have in the farm.
All right. Thank you very much, Ricardo, for the fascinating seminar and all of the interesting conversation around this topic. As a reminder, I'd like to thank everybody for attending our presentation. And I would like to remind everybody that, again, next Wednesday on the 19th, we will have Sumit Singh from the PG&E looking at their PG&E's approach to balancing resiliency, reliability, decarbonization, and climate change. Again, thinking about moving toward that zero emission future. So please check out our website for more information about that talk. Today's talk will be available for viewing tomorrow afternoon on the CITRIS YouTube website web channel. So please take a look at that. And if you have any other questions for our speaker, please feel free to reach out to the CITRIS office and we'll make sure to get you in touch with them. Thank you.
Thank you. Bye-bye.
Thank you, Aaron and Ricardo. That was a great talk.
Thank you, Laurie.
Thank you both.